Good morning, class. Today we're going to talk about estimation and graphs. And so this should not be really new information to you. And so hopefully there won't be any problems. If you're following along in your book, this is going to start on page 13. So I'm going to read page 13 to you real quick. It says, if present trends continue, is it possible that our descendants could live to be 200 years of age? To answer that question, we need to examine data for life expectancy and develop estimation techniques for representing the data mathematically. In this section, you will learn estimation methods that will enable you to obtain mathematical representation of data displayed by graphs, using this representation to predict what might happen in the future. Estimation is the process of arriving at an approximate answer to a question. For example, companies estimate the amount of their products consumers will likely use, and economists estimate financial trends. If you are about to cross a street, you may estimate the speed of oncoming cars so that you know whether or not to wait before crossing. Rounding numbers is also an estimation method. You might round a number without even being aware that you're doing so. You might say that you're 20 years old rather than 20 years, 5 months, or that you'll be home in about half an hour rather than 25 minutes. You will find estimation to be equally valuable in your work in this class. Making mistakes with a calculator or a computer is easy. Estimation can tell you whether the answer displayed for a computation makes sense. In this section, we demonstrate several estimation methods. In the second part of the section, we apply these techniques to information given by graphs. Performing computations using rounded numbers is one way to check whether an answer displayed by a calculator or a computer is reasonable. Rounding whole numbers depends on knowing the place values of the digits. And then the rest of that goes through and tells you the digits. In case you didn't know, they're down there in blue. Where's the millions? Where's the billions spot? And so on. Okay, so estimation is the process of arriving at an approximate answer to a question. Your next question is, why would you approximate? So here are some examples of why you might use approximation. Maybe it's a tip and you had good service and you want to leave a big tip and you say, well, I'll leave 20%. How can you calculate that? Or maybe it was bad service and you want to leave a small tip and 10%. How could you calculate that? Or maybe you're at the grocery store shopping and you don't have anything more than cash in your pocket, and you don't need to make sure that you don't go over how much cash you have. So as you're shopping, you can change the numbers of how much everything costs, and you can get an estimate of what you might be able to buy. It might tell you whether you have to put the Oreos back or do you get to keep them. If you were planning a party, some things that you might estimate would, of course, be, how many people are coming to the party. Do you have enough food for the people at the party? Is your venue big enough? Are there going to be enough chairs? What time people might come? What time they might leave? So how long they would stay? Things like that would be something that you could estimate. Time, we always estimate our time. Of course, the example they gave us is maybe how long does it take us to get home? And we always, say half an hour or an hour. We usually don't say it takes us 13 minutes and 22 seconds. So those are things that we can estimate. Timing, maybe as you're driving. Do you have enough time to get through the yellow light before it turns red? Or how long, if you have a project, how long is it going to take you to do your project? And can you procrastinate, or do you need to start working on it at a specific time? So maybe you can think of some others that go along with these, and then maybe you could write down some other things that you might estimate. In class, we talked about how you could estimate maybe what your grade is, or maybe you know what your grade is, but you need to estimate what the next grade on your test has to be in order for you to keep a passing grade. So there are lots of different things that we approximate in our everyday lives. And so rounding, what's the difference in rounding and estimation? Estimation, again, is an approximate answer, but rounding actually has rules. So that number 5 is a magic number, and whatever number I'm here, so if this is the tens or the hundreds or the millions or whatever it is, the number to the right is the one that we look at, and if it is 5 or greater, then this number goes up. If it's less than 5, then this number stays the same. So technically, there's no such thing as rounding down. I know we say that sometimes, but we don't actually make this number ever go down. It either stays the same or it goes up. So as we look at the examples in the book, this is on page 14, it goes through and it says what is the nearest million. So we look at our place values, and the 1 here is in the million spot. So we look at the 5, that would make this go to a 2. So it'd be 6, 7, 5, 2, and everything else turns to zeros. Okay. If we looked at the thousands, we look at the 1,000 spot, then the 1,000 spot is here for the 3. We're looking at the 1. So we would get 6,751,593 because it doesn't change it, and then 0, 0, 0. Okay. If we're looking down here, this is pi, but this is our decimal, so all of these end in a TH. And so this one says the nearest hundredth, so tenths, hundredths, so we're looking at the 4, and the 1 is going to make it stay the same, so this would be 3.14. And then if we were to look at the next one, it is the thousandth spot, so tenths, hundredths, thousandths. The 5 this time is going to make that go up, so we'd have 3.142 as our answer. Okay. At this time, I'm going to ask you guys on your notes to do checkpoint 1 and 2. So if you'll pause the video and then come back and check your answers. Okay, welcome back after you've paused that. In checkpoint 1, it asks you to round the number. And so your first one to the billion is going to be 7 billion. A. And then in B, round to the 100 million. So you should get 6,800,000,000. There we go. And your C question says round to the nearest 10,000. So you should get 6,751,590. So there's your 3 answers for checkpoint 1. And then checkpoint 2, in A, it asks you to round to the nearest tenth. It used pi again, so 3.1. And question B is the nearest 10,000th, so that's 3.1416. So those are rounding to the correct place value. All right, so next we have, just like we said, an example might be going to the grocery store. So we can look at this and we can change this. We could change it to $3. We could change it to $2.60. We could even change it to $2.50. None of those are wrong. None of those are wrong. Some of them just might be better than others. So as you go through and you look at each one of these, maybe this one's a 2 and a 3 and so on. So maybe as you look at it, these are your estimations, and your total was $15 when you estimated, and the exact total was $14.67. So you had a good estimate here. It's just maybe you forgot about tax. So maybe you shouldn't have made this go down or this one go down. Maybe they should have gone up, and we could have covered our taxes on that. But it doesn't make this wrong, okay? So between estimation on the test, you have to tell me, just like this shows me what I estimated to, and then add them up, and there's your total, okay? Don't ever give me the exact number on the test when it asks you for an estimation, because those are two different things, okay? All right, so you guys try checkpoint 3. If you'll go ahead and pause your video, and then you do it and you can come back. So checkpoint 3 says round each cost to the nearest dollar. So you should have gotten 2, 1, 5, 4, 1, 2, and 3 for a total of $18. Now, when we add all those up, question B says, is 2185, does that make that a good estimate? And we would probably say no, okay, because we didn't have enough money to cover it. So if the total cost would have been $21.85, then what we estimated would not have been a good number. All right. Example 4 here says that your paycheck, this is something you could estimate how much money you're going to make for whatever reason. Do you have enough to cover your bills, or do you have enough to buy your Xbox that you want? So here we have a worker who does $28 an hour, and we want to know what he makes for a weekly salary and then a yearly salary. So in a week, normally someone would work 40 hours a week, and in a year, there are 52 weeks in a year. So we could say the $28, we could change that quickly to a 30 or a 25, because those are easy numbers because they have a 0 and a 5. Those are easy numbers to multiply with. And when we multiply those out, we could say 40 hours a week times 30 hours, so I make about $1,200 a week. And if I make $1,200 a week, instead of using 50, instead of using 52, you could change it to 50 hours or 50 weeks, and you could have $1,200 times your 50 weeks gives you a yearly salary of $60,000. So we could come up with that quickly in our head. All right. So you guys are going to try checkpoint 4. Go ahead and pause your video. So checkpoint 4 talks about a landscape architect, and he makes $52 an hour. And so I would probably change that to 50. And then again, it's the same number of hours in a week, so times 40. So I would say he makes about $2,000 a week. And then again, the same question for a year. And so I would take 2,000 and multiply that by 50. And so this would be my A question. And then he would make about $100,000 a year at that estimation. Okay. All right. We already talked about how tipping can be an estimation. In class, we discussed what actually might be a good tip versus a bad tip, and quickly coming up with what we could leave or quickly in our head. I think I think 15% is still a good number for a tip, and 9.75% is our tax in Putnam County. And so we could estimate this to 10%, and then we could say, oh, well, I could take the tax plus half the tax. And that would be one way that I could come up with 15%. If we said it was 20%, then we could just say the tax of 10% times 2, and we would get 20%. So there's different ways in your head that you could quickly come up with how much to leave for a tip. All right, then the last little part of the section talks about estimating with graphs. And so a circle graph is good to show how a whole quantity is divided into parts. And last week we talked about sectors on that ACT sheet. And so each one of those sections are called sectors. A bar graph, these are convenient for showing comparisons among items. You can tell which one is the tallest, which one is the shortest. Do any of them look about the same? And then line graphs are often used to illustrate trends over time. This would be like the stock market because it changes so often. So you look at line graphs for trends over time. Okay, so on page 17, let's run through examples 5, 6, and 7. Each one of these. The first one is a circle graph, and we would read this, and the question says, according to the circle graph over on page 16, we want to use the appropriate information displayed by a graph to determine a calculation that shows the number of Americans 20 years and older who define old age as decline in physical ability. So when I look over the circle graph, that's in blue, and it's 41%. And it told me in the total population is 220,948, 220 million, sorry, 948,915. And so the exact would just mean that I multiply those two. But it wants me to find the exact, and then in the B part, it wants me to actually estimate. So here is the A part, and we would just multiply those out, and we would come up with 200, 41%. On the B part, we're going to do an estimate. So we're going to change this to 40%. And we're going to change this to 200 million or 220 million or even 221 million. All three of those are completely fine when you multiply that out, okay? So any one of those is going to give you 80 million or 88 million or 88,400,000. So when you multiply those out, but you should be able to do those quicker because of all the zeros that are there. You should be able to do those quicker, and that is a good estimation. All right, so pause your video and you guys can do checkpoint 5. So checkpoint 5 uses the same graph, and this time it asks you to do the people who said mental function, decline in mental functioning, which is the green. So it's 32%, and the population changed to 21,728,978. Okay, so we would take that and you would multiply it and get the exact amount. Remember, I don't think I mentioned it above, but that has to be 0.32. We have to use decimals. We can't use actual percentages. And then the B part says that we're going to estimate. So I'm going to change this to 30%. And I'm going to change this to probably 20 million or 21 million or even 22 million. Any of those would work, and you multiply those out and you come up with 6 million or 6,600,000 or 6,000,006, I don't know. Oh, 6,300,000. So any one of those would work for changing and making good estimates. All right, let's look at number 6. So number 6 has a bar graph, and this one wants a man's increased life expectancy rounded to the nearest, so the men are in orange. So that is also known as a slope, rate of change, y minus y over x minus x. So we would take the largest male number, which is 75.2, and subtract the smallest male number, which is 66.6 over the total years, and that would be the year 2005 minus the year 1960. And what we get here is going to be 8.6 over 45 years. So we need to know that this is 8.6 years increase over a 45-year span. And then we would divide that out and we would get 0.19. And again, it's not it's over 1. You don't have to put the 1 there, but this just means that for every year I go over, I'm going to go up 0.19 years or a month and a half or something like that. So that's what this number is talking about. Okay. Oh dear. All right. So this is what we have for our slope or our life expectancy increase. And then the B question says, what would it be if we were looking at the year 2020? So I can use this information and write it in slope-intercept form. And I would say, well, I started at 66.6, and every year I add 0.9, and I'm going to add it until the year 2020. And 2020, let's see, 2020 is 60 years after 1960. This is where we started, and this is where we want to go. So it's 60 years. So when I plug that in, I end up getting the years, 78 years old is what we expect somebody to live when they are born in the year 2020. Okay, so you guys can pause and then do checkpoint 6 and then come back and look at it. So checkpoint 6 is using the same bar graph, except this time it is for women. So for your A, you should have gotten 0.16, and for your B, you should have gotten 87.5 years old. This is doing the same thing up here. The only thing that's changed is for the women. The highest year was 80.4, and the small year was 73.1. And the years stay the same, and so when we divide all that out, we end up with 0.16, and then we plug it in, so our change would be 73.1 plus 0.16 times, and this time we were going to the year 2050, which was 90 years later. Okay? All right. I'm going to have to pause my video for just a second. As soon as I find the file. Okay, so sorry about that. Didn't mean to pause it real funny. So we're on example 7, and this one is on page 19. So if you're looking at the book online, then this one says the line graph over to the right shows the percentage of high school students who use alcohol or marijuana during the 30 days prior to being surveyed for this study. Question A, find an estimate for the percentage of seniors who used marijuana in 1990. So you're going to go to the red line, you're going to go over to 1990, you're going to go up to the dot, and you're going to estimate that that is about 14 or 15%. Question B says, in which 5-year period did the percentage of seniors who used marijuana decrease at the greatest rate? So if we're looking for increase or decrease, we're looking at the slope, the slant of each part of the line or each section of the line graph. And since it says the greatest rate, then we're looking for the steepest slope up there. And so marijuana, again, is the red line. So if you look at between 1985 and 1990, that would be the steepest slope available in a 5-year period. And then the C question says, in which year labeled on the horizontal axis did 50% of the seniors use alcohol? So this time we're looking at the blue line. So we follow up 50% on the y-axis, and then we go over, and there's really 2 dots that are close, but the year 2000 is on it. But if you said 1995, that's still a good estimate. So I would take either one of those if I were asking you that in class. Okay? All right, so now you're going to try checkpoint 7. So you can pause the video, and then we'll come back and discuss those. All right, so on A, it says find an estimate for the percentage of seniors who use alcohol in 1985. So we're looking at the blue line over to 1985, going up to the blue dot, and we would say about 66 or maybe 67%. Question B, in which 5-year period did the percentage of seniors who used marijuana decrease at the slowest rate? So now we're looking for the red line, but we want it to decrease very slowly, so not steep at all. So if you look at the years 2000 to 2005, there is a decline, and it's very slow. So that would be our 2 years, 2000 to 2005. And then the C question, In which year, labeled on the horizontal axis, did approximately 57% of the seniors use alcohol? So this time we're using the blue line again. We're going all the way up to 57%. We're having to estimate it in there. Over to the blue dot, and that looks like the year 1990. And so that would be our answer. All right. Last little part here is changing or writing a mathematical model from a formula. So the process of finding formulas to describe real-world phenomena is called mathematical modeling. A formula that is a statement of equality that uses letters to express the relationship between two or more variables. So this would be like y equals mx plus b. That's a formula. And then if we change it over to mathematical modeling, we're going to change the y and the x to letters that just represent the items that we're talking about, the real world items. So there's not really any difference between the two things, but when we say mathematical modeling, we are talking about real life phenomena. All right, last example here, college education. If we looked at example 8 at the bottom of page 20, it says the bar graph over on the other page shows the average cost of tuition and fees for public four-year college adjusted for inflation. Question A, estimate the yearly increase in tuition and fees, round that to the nearest dollar. So that one is, again, slope, rise over run. So we're going to take 6185 minus 3362 over 2008 minus the year 2000. So when you look at the graph, it's the small bar and the big bar. So instead of taking an actual average where we added them all together and divided, we're going to take the biggest minus the smallest. And so biggest minus smallest is going to give us a positive. So this gives us 2,823 over 8 years. And that reduces to about $353 per 1 year. So on average, we're saying the cost of tuition goes up $353 a year. So then it says write a mathematical model using T as tuition. And so we would take our beginning number. We always start from the beginning. So 3,362 plus the $353 every year. And we want to know, we don't know how many years, so we can interchange that X with however many numbers we want. So that's the B part. That is your mathematical model so that you can predict whatever you want, whenever you want. All right, then the last part, C, says we want to use this and figure out what does it cost in the year 2014. So the year 2014 is 14 years after the beginning of the whole graph, so the 2000. So we would plug in the number 14, and when we calculated all that out, we end up getting $8,304 for tuition in the year 2012. All right, now if you'll go ahead and pause it for the last time, you guys are going to do checkpoint 8 on page 22. Okay, so if you've come back and you've done checkpoint 8, this one is for private schools instead of public. And so this is 23,712 minus 15,518. And when we subtract all that, we end up getting, actually, I don't even know. Let me multiply, or let me subtract that up real quick. So we got 23,712 minus 15,518. 8194. So 8194. Now the nice thing is the years stayed the same, so it's still 8 years. And then when we divide that out, we end up getting 1,024. So $1,024 per year for private. Okay. So when we take this information and we go and we plug it over here into our tuition, Tuition costs, again, from the beginning, $15,518 plus $1,024 every year. Then that is our mathematical model for a private school. And then the C question says, all right, what are you going to do in the year 2012? So in the year 2012 is 12 years after. So we're going to plug a 12 in to the whole formula. And when we get the answer, we get $27,806. So $27,806 is what we say tuition will cost at a private school in the year 2012. Okay, so I hope everything is going well once you've listened to this and seen all the examples. And here is the assignment for this section. So if you'll do those, you can come in and check them with me whenever you get them done if you are looking at this when you're absent. So, all right, thanks a lot. Talk to you guys next time.